Hello everyone, and welcome back to chapter 21. In this video we're going to continue with the equation that we came up with in the last video, which was Coulomb's law. And Coulomb's law was what allowed us to find the magnitude of force that exists between two charged particles. And so Q1 and Q2 are going to be the charge values of two particles in our system. R will be the separation distance between those particles, and then K is our proportionality constant. And this is a universal constant between any two charged particles, and that is going to be approximately 9 times 10 to the 9th. And then the units on that were Newton meter squared per Coulomb squared. And we've already seen one example of the force between two charges, or what we could call the Coulomb force. And the last video we actually used two protons. But in this video, what I think we'll try is a proton and an electron. Now, if you remember, in the previous video, we also talked about the fact that charge is quantized, which means that electric charge does have a minimum value, and that is what we called the elementary charge. That was 1.6 10 to the minus 19 coulombs, so that was the smallest charge that we could have, at least for this class. And both the charge of the proton and the electron have that magnitude. The only difference is that the proton was going to have a positive value and the electron would have a negative value. And here, when I write down the letter E, what I'm really specifying is that this is the elementary charge. So now we want to figure out what is the force between the proton and the electron. Well, if they both have the same charge magnitude, then how would this be any different from the two proton example that we saw in the last video? The only difference between the proton and the electron is the charge and the mass value. And as we saw, mass did not play a part in the electric force expression. So if it's just a matter of the charge magnitude, then the only difference that I should see between these two examples is the minus sign from the electric charge of the electron. And so if I introduce a minus sign into our force expression, then we should just end up flipping the direction of our force vector over. And so that's what we need to discuss today. Now that we have this equation in front of us that allows us to find the magnitude of the force, now we have to figure out what the direction of the force is. And since force is a vector, those are the two pieces that we need. We have to have magnitude and direction. So to help us out with that, we're going to use a very famous saying, which I'm sure you've all heard at some point or another, and that is that opposites attract. Opposites attract. There we go. So if I have two oppositely charged particles, like a proton and an electron, those particles are going to attract one another. So what that means is that if they're going to attract, if they're going to come together, then there have to be forces acting on those particles, pulling them towards one another. And that force, the force that's acting on each of those particles, will be the electric force that we have right up here. So we have the two different charges, we have the separation distance between them. I'll go ahead and put in a separation distance here. And so we can get the magnitude of that force by plugging all the values in. And then the direction of the force, well, now we have two forces in the picture. So which way is the force supposed to be pointing? And the answer to that is that since we have two particles, each particle has its own force acting on it. So each particle will have its own direction assigned to the force that is acting on it. The only way that we can have these particles attract is if the force on the proton points to the right and the force on the electron points to the left. So it's actually quite easy for us to figure out what the direction of that force needs to be simply by using our statement here that says that opposites attract. Now, the fact that we have two forces here is actually a result of a Physics 1 discussion. If we remember the third law, Newton's third law, which said that for every force there is an equal and opposite counterforce. And that's exactly what we have here. We have two forces of the same magnitude, but they are pointing in opposite directions. So we do in fact have the equal and opposite attributes here to these forces. And so if opposites attract, what happens if we have two particles that are of the same sign? So what happens if we have two protons? Well, if opposites attract, then like particles are going to repel. And so these two protons, they have the same charge, they don't like each other, they're going to repel, and so we are going to see equal and opposite forces repelling those two charged particles from one another. Now, why do we have these statements? What causes opposite charges to attract and like charges to repel? Well, it actually has to do with the fact that the universe does not like large concentrations. And so if I had a very large concentration of let's say water, let's say I had an aquarium and I put a partition in between the two sides of the aquarium and then I fill up one side, that water will stay there on that side as long as the partition is there. But the moment I remove the partition, that water is not just going to stay there. It wants to spread itself out. It wants to redistribute itself. It wants to go from that higher concentration to a lower concentration. And we're going to see the same thing with charged particles. We do not want to see particles of the same sign notation coming together to form a greater concentration of positive charge. Likewise, we would not expect to see negatively charged particles coming together to form a larger concentration of negative charges. They would also repel one another. But if the charges are of opposite sign, bringing those two charges together, a positive charge and a negative charge, does not result in a higher concentration of charge. In fact, it results in a lower concentration of charge, because if we add together the sign values of those charges, we actually get something that approaches zero as opposed to a higher concentration. And so this is the reason why we have the opposites attract and the like repel. The universe is effectively trying to spread out all of this charge. And so now that we have that idea, let's discuss one more piece of information. I'm going to go ahead and draw these two particles in different positions here. So before we had our particles all basically along these horizontal axes. Trying to draw a dashed line with my stylus. It's not quite working. There we go. So these dashed lines that I've drawn here, these are what I'm going to call the line of sight. And so looking directly from one particle to the other, that would be the line that you would look along. And as you can see, the forces, whether they're the attractive forces or the repulsive forces, lie along that line of sight. And that's also going to be helpful in determining what direction these forces need to point. So now that I have these two protons sitting out in space, and I want to know what direction will the resulting forces be pointing in. To do that, all I need to do is sketch myself a little line of sight between those two particles, and then I think back to our little catchphrases: opposites attract, like repel. These are protons. They have the same sign notation, so they are like charges. That means they need to repel one another. We need to see our forces point away. And now we need to put everything together. Now that we know how to determine the direction of force between two charged particles, and now that we know how to find the magnitude of force between two charged particles, we need one more thing to ensure that we don't sabotage ourselves in the math. And when I say sabotage, here's what I mean. If I have the case scenario of the proton and the electron, so I'll just draw those two over here. With a proton and an electron, I know that these particles are going to attract. I know that the forces need to be pointing towards each other. So that part's taken care of. Now I go to figure out the magnitude of those forces. And so I take my K value. And actually, I'll go ahead and plug the actual values in. My K value was 8.99, 10 to the 9th. I have charge 1, which I'll go ahead and let that be the proton. 1 elementary charge, 1.6, 10 to the minus 19. We have charge 2, which is the electron, which is negative 1.6 10 to the minus 19. All over the separation distance, which I haven't specified what that's going to be, but we'll just let that be a meter. So all over r squared, which is 1 squared, which is 1. All right, so I take all those values, I plug them into my calculator, and, well, everything in the numerator after I finish taking the products is going to result in a negative. And whenever we have a negative, that means opposite, basically. So does that mean that I have to come back down here, up here? Does that mean that I have to come up here and then flip around the forces again? And the answer is no. We already have the direction of the forces established. These are opposite charges. We know that opposites attract. And so those force directions, those are done. Those are the directions of the forces. What we don't want to happen is this. We don't want to bring any unnecessary negative signs into the math, because then we might be tempted to change something. So the way that we're going to carry out the math from our force expression so that we don't make the mistake of flipping our forces around, you'll notice that here I've written force magnitude, and magnitude is always the absolute value. Whether it's positive or negative, we just take the absolute value. And then we let the diagram tell us what direction that force needs to be pointing. And so we're going to modify Coulomb's law to use the magnitudes of the two charges. So Coulomb's law, as it is written now, will only provide us the magnitude. This equation does not provide us the direction of the force. For that, we need to come back to these expressions down here and just ask ourselves, are the charges going to attract or repel based on their sign notation? And so that's how we're going to use Coulomb's law from now on. We're going to use only the magnitude. Now you can go ahead and crunch the numbers on this, and at this point it's a good idea to discuss how we want to use our calculator. Different students have different models of calculators. Some of you might even be using your cell phone with some kind of calculator app. But you'll notice here that everything in this statement is either a really large number or a really small number. And I have some students that try to cram everything into their calculator at once, then hit the enter button, and when you do it that way, you run the risk of having some kind of mistake in your entries for the calculator. And so what I would recommend that you do, especially since you have all of these power terms, remember your algebra, and remember that when you are taking, and this is now going to be a positive since we're dealing with magnitudes only. In fact, let's, for this discussion, let's work with a fresh example. Let's take charge 1 as, we'll say, 20 microcoulombs, and charge 2 can be negative 50 microcoulombs. and they are separated by 5 centimeters. And I want to know the magnitude of force between these two charged particles. Now the microcoulomb, the micro is 10 to the minus 6 for its notation. And so what we need to do now is plug all of this into our equation. We have K, magnitude of Q1, magnitude of Q2 over R squared. 8.99, 10 to the 9. So Q1, we need magnitude. So positive 20, 10 to the negative 6. Q2, we need magnitude. 50, 10 to the negative 6. All over 0.05 squared. Now, I'm going to take this and I'm going to rewrite it as 5 times 10 to the minus 2. And I have a reason for doing this. And remember, we're going to square that. So now, you have to put all this in your calculator. And if you try putting all of that into your calculator the way it is, all it's going to take is one little slip of the finger, or a missing parenthesis, or an incorrect sign notation, and then we have the wrong answer. So what I want to do is show you a way of trying to minimize the chances of making a mistake with your calculations. Every single term in here is either a product or a division. So the stuff in the denominator, that's technically division. Everything in the numerator is a product. Back in algebra, we had a certain set of rules when it came to taking the product of like bases, or dividing by like bases. Let's call this x sub p. And so if I had something like this in an algebra expression, we could take the powers and we could add them together if they were products, and we could subtract them if they were divisions. And so we can very easily combine those power terms into a single term. And I have 4 different terms here. If I can remove all of those power terms and combine them into one, then the only thing left for me is to combine the actual numerical values. So let's go ahead and combine all of the power terms right now. I have 10 to the 9th, I have a 10 to the minus 6, 10 to the minus 6, and down here, that is 10 to the minus 4. So everything in the top will be added together. Now we do have some negative powers up there, but we're still going to add them. We have 9 plus a negative 6 plus a negative 6, which makes for negative 3. And then we have the division. So now we need to take the top power and subtract the bottom power. We have negative 3 minus a negative 4. So that's going to result in just a positive 1. So all that I was able to do without my calculator. I could do that in my head if I had to. And so I know that I'm going to have a power term of 10 to the minus 1 as part of my answer. And now I can use my calculator to combine the remainder. I have my 8.99 times 20 times 50, all divided by 5 squared. Don't forget that square. And that gets me 359.6 times 10 to the 1, or 3,596. And we are solving for a force, so this will be in newtons. Right? So the only thing that you should really have to put into your calculator are the numerical values. And then those power values, you can just take care of those on the side. And that means that you don't have to enter all of that extra information into your calculator and risk getting an incorrect answer. Okay, so now that we've seen how Coulomb's law is going to work for like charges, for opposite charges, what we want to do now is apply Coulomb's law to a larger system of particles. So what I'm going to do is make ourselves a reference frame. We have an XY reference frame. And I'm going to place 4 different particles in this system. Go ahead and make some marks here, and we'll say that each of these marks is a centimeter. So both of our axes are measured in centimeters. The first particle, I'm going to put that right at the origin. Second particle, I'll put right here. Third particle will go right here, and the last particle will be right there. So what I have is a rectangular system of particles, and each of these particles will have a charge associated with them. 1, 2, 3, and 4. And off to the side here, we can decide what we want those charge values to be. We'll do 10 microcoulombs, negative 20 microcoulombs, negative 30 microcoulombs, and positive 40 microcoulombs. So we have 2 positives and 2 negatives. And we can see what the separation distance is between any 2 given particles based on our reference frame. And what I would like to know is what is the net force acting on one of these particles. And for that I'm going to have to choose. So if you want to pick one of these at random, you can. We may as well go for the charge that's sitting at the origin. It really doesn't make a difference which one we pick, just as long as we pick one. So I want to know the net force that is acting on particle 1. And you'll note that I wrote that as net. And this has essentially turned into a physics 1 problem. If I'm going to find the net force acting on something, then I need to take all of the then I need to take the summation of all of the individual forces in the system that are acting on charge 1. Now, charge 1 has 3 other charges in the system that it can interact with. And so that means there are going to be 3 forces that I need to combine. There will be the force of charge 2 acting on charge 1. There will be the force of charge 3 acting on charge 1. And force of charge 4 acting on charge 1. So we're going to add those 3 forces together. That will provide us with the net force. But we need to keep in mind that forces are vectors, and any vector needs to have magnitude and direction. Each of these forces will have its own magnitude and direction. It's then going to be our job to combine them using the proper vector math to get that net force. So, first things first, let's take what we learned up above about opposites attract and like repel, and using these line of sight ideas to figure out the direction of the forces. The force between charges 1 and 2. So we have charges 1 and 2, and charge 1 and charge 2 have opposite signs, which means they will attract. So what I need to do is draw some force lines that show charge 1 being attracted to charge 2. And then we might be tempted to draw the force line that shows charge 2 being attracted to charge 1. And that force does exist, but the only thing that we're concerned with right now is what is happening to charge 1. Okay, this force up here is not technically acting on charge 1. I already have that force. It's right here. And so this is the force of charge 2 on charge 1. It's pointing straight up along the y-axis. Let's go ahead and find the directions of the other 2 forces, and then we'll talk about the magnitudes. Charge 1 and charge 3 also have opposite signs, and so we need to have a force that shows charge 1 being attracted to charge 3 right along the line of sight. I do not need to show the attractive force that is acting on charge 3 because, again, we're not interested in what's happening to the other particles. We just want to know what's happening to charge 1. So there is force of charge 3 acting on charge 1. And then the last one is the combination of charge 1 and charge 4. Now, charge 1 and charge 4 have the same sign notation. And so charge 1 will have to be repelled away from charge 4. Charge 1 and charge 4 have a line of sight right here. And I'm going to use that to help me line up the repulsive force. I need a force that's going to take charge 1 away from charge 4. And the reason why it's going to be so important for us to know the directions of those forces is because when we go to add everything together, I can't just take the magnitudes of those 3 forces and add them together. We have vector directions that we have to consider. And because we have an XY axis here, the better option for us in trying to figure out the net force is actually to start working in those x and y directions. So if I want to know what the net force is that's acting on charge 1, my best bet is to figure out what the net force in the x direction is, then figure out what the net force in the y direction is. I can then combine those to produce the two-dimensional version of the net force. So essentially we're looking for the components of the net force in the x and the y direction. And the way we're going to do that is we're going to use the x and y components of the respective forces that we're adding together. So again, this is just a Physics 1 problem now. A lot of subscripts here, but they're necessary so that we can keep everything orderly. Alright, so I need to know the x components of all of these vectors, and I need to know the y components of all of these vectors. Hence the reason why we needed to know the directions that they were pointing. Now, force 2-1 and force 3-1, those are easy because both of them exist in either the x or the y direction. But force 4-1, that's a little bit more challenging because, as we can see, it is pointing in both the x and y directions at the same time. So it's going to be our job to figure out what the x and y components of that vector are going to be. Now we can do that because right along this line of sight that we had drawn, we can measure an angle relationship. Oops. Between the x-axis and where that line of sight is. And, well, actually, I'm going to move these components of force 4-1 here so that I can take advantage of the fact that I'm going to move the Q1 so that I can take advantage of the fact that angles of opposite vertices are the same. So by being able to measure the angle relationship between our line of sight between charges 1 and 4 and the x-axis, I now have an angle that I can use to break up force 1-4 into its x and y components. Alright, so first things first, I need to figure out what that angle is. What is angle theta? Well, angle theta is part of a right triangle, which is made up of the dimensions of this rectangular distribution of charges. I have an x value of 4, so we've got 4 centimeters on the x-axis and 6 centimeters on the y-axis. And so using some trig, we can take the inverse tangent of 6/4, opposite over adjacent, to tell us what theta is going to be. So 6 divided by 4 is 1.5. We need a tangent of that. And, oops. And my calculator is not working right now for some reason. So I'll have to try something else. Oh, that's why I was not using the inverse. There we go. 1.5. There, that looks better. 56.3 degrees. So we have 56.3 degrees. For theta, we're going to use that same theta value to break up our force vector F41. But in order to do that, we need to have some magnitude for that force. Not only that, we're going to need magnitudes for the other forces in the system as well. So let's take a break from all of the vector math here, and we will use Coulomb's law to help us find the magnitudes of these forces. So we'll start with force 2-1, which would be K, Q2, Q1 over. Now I'm going to also introduce some subscripts down here because the separation distance between each set of charges is not the same as all of the others. The separation distance between Q1 and Q2 is 6 centimeters. So we need to make sure that when we put all of these numbers in here, that we're using the correct separation distance. And let's see, for charge 2 we had magnitude 20, 10 minus 6. For charge 1 we have 10, 10 minus 6. And that is going to equal, well, remember the little trick that we had before. If we add together the if we add together the powers, 9 plus -6 plus -6 is -3. And all that leaves us is to take the product of the values in front. We have the 8.99 times 20 times 10. That's 1798. And then we have to divide that by 0.06 squared. So that's going to cut down considerably on the stuff that we have to enter into our calculator. And I am getting, let's see here, just shy of 500, but I'm going to go ahead and bump that up to 500. So we have 500 newtons of force for F21. For F31, K, Q3, Q1, R31 squared. We have our K value. Q3 was magnitude 30. Q1 was still magnitude 10. And the separation distance between charge 1 and charge 3 is 4 centimeters. So 0.04. Now we have exactly the same power terms here as what we did in the previous example right above. So we're still going to get 10 to the minus 3, but now we have 8.99 times 30 times 10, which is going to be 2697, all divided by 0.4 squared. Forgot the squared there. And our calculator is going to give us a value of approximately 1686 newtons. One more time. Now we need magnitude force 1,4. Charge 4 was 40 microcoulombs, so again magnitude. Charge 1 is still magnitude 10 microcoulombs. And, well, now I need to know what was the separation distance between charge 1 and charge 4. That's something we haven't figured out yet. Along the line of sight, that's actually the hypotenuse of the right triangle that we've been using, which has side legs of 4 and 6. So our Pythagorean theorem says that square root of the sum of the squares will give us the value of the hypotenuse, which I'll just go ahead and call that little r, is approximately 7.21 centimeters. And so that is the value that we will need to use down here so that we can figure out the magnitude of force. Now, again, we have all of our powers in the numerator that are going to reduce down to 10 to the minus 3. The values in the numerator, if you notice, the only difference between this and the first line is that we should have twice as much. So instead of the 1798, we should have 3596, and that's going to be divided by our 0.0721 squared. Times our 10 to the negative 3 power is resulting in approximately 692 newtons. Alright, so we have our magnitudes for the respective forces, force 3.1 and force 4.1. Thought the highlighter was bigger than that. So these are the values that we need to use in our sum of forces expression. Starting with the net force in the x direction. When we look at our diagram, force 2.1 is all in the y-axis, and so we don't have an x component for force 2.1. I can put in a 0 for that component, but still I don't have a value. All of force 2, 1 is actually in the y direction, and so I'm going to put the full value of force 2, 1 in the y summation. Force 3, 1 is all in the x direction, and so I can put all of force 3, 1 in the x direction. Force 3, 1 does not have a y component, and so I put a 0 down there for the y component. Force 4, 1 does have x and y components, as we can see over here on our diagram. And those two components, force 4, 1x, force 4, 1y, we're going to find those based on the angle relationship of 56.3 degrees. So time to put all of that information together. We have our 56.3 degrees that we need to apply to the magnitude of force 4, 1. And I'm just going to draw a quick little sketch of what force 4, 1 looked like along with its components. And you'll notice from the XY reference frame, both of these components are pointing in the negative directions. And so we are going to have to incorporate that into our values. So I'm going to put the minus signs in there right now so that I don't forget them. Force 4, 1x. This is the side of the triangle that is adjacent to our angle. So we're going to need to use cosine. F41 cosine of theta. And that means that the y component, being the leg opposite of our angle, we'll have to use sine of theta. And now we'll put our values in here. We have magnitude 692 with a minus sign out front, cosine of 56.3 degrees. And that is going to equal, plug that into our calculator, negative 384. And for the y component, we have sine of our angle, and this is coming out to be negative 576 newtons for units. So now we're going to bring those values up. The x component of force 4, 1 was negative 384. The x component, or excuse me, the y component of force 4, 1 was negative 576. And we can finally add everything up. For the x component of our net force, we have 1302, and for the y component of our net force, we have a negative 76. So as we said, we can now put those values together as the components of the net force that are acting on charge 1. We have the x component of 1302, and the y component was negative. So I'll just put that in as a negative 76. Now, having your force represented in component form is perfectly okay. In fact, it's my preference as to how vectors should be represented, but from time to time the book is going to ask for magnitude and direction of your force. And so magnitude of any vector, you have your magnitude mantra, which is square root of the sum of the squares. So we're going to take the square root of the sum of the squares of our components. 1302, negative 76. Now, anytime you square something, you're going to lose the sign notation. So any magnitude should be positive. And I just want to double check my calculations here. We have 1302 squared plus 76 squared. Square root of that comes out to be 1304 newtons. The angle for any vector can be found by taking the inverse tangent of the y component over the x component. And so we have negative 76 over 1302. And we need an inverse tangent of that value. And I'm getting a negative 3.3 degrees. So a very shallow angle. But we should ask ourselves if that angle makes sense, because depending on how you enter values into your inverse tangent, sometimes your calculator doesn't know that you're actually looking for the angle of a given vector, and your placement of a plus minus sign inside that ratio can confuse your calculator. So what we want to do is just take a look at the components that we have for our net force. I have an x component that is positive. I have a y component that is negative. And so this is what the direction of our net force should look like. And in terms of angle, negative 3.3 degrees, that is the direction of negative angle measure, so that looks right to me. And the fact that we have such a large x component compared to the y component also says that that should be a pretty shallow angle right below the x-axis. Alright, well, I understand that this is a pretty lengthy example problem, especially since the majority of it was Physics 1. But that's kind of the point, was that we go through this to refresh ourselves on the ideas of summation of force, breaking up components using the trig, putting them back together using the trig and Pythagorean theorem. And now that we have found the net force that is acting on charge 1 in our system, it would be a valid homework problem or test problem to ask you to find the net force acting on any of the other charges in the system. Now, please do not make the mistake of thinking that all of these charges are going to have the same net force acting on them. This was the net force acting on charge 1 because of the way that charge 1 was interacting with all of the other charges in the system. The way that charge 1 and charge 2 interact is going to be different from the way that charge 2 and charge 4 interact. And the way that charge 1 and charge 3 interact is going to be different from the way that charge 3 and charge 4 interact. So all 4 of these charges should have unique net forces that are acting on them. And the way that we would find those forces would be to go through this process once again, mapping out the directions that those attractive and repulsive forces need to be pointing, and then going through and figuring out what the individual magnitudes of force between those particles is, so that we can put everything together in our vector math and get the components of a net force. So we're going to go ahead and end the video there for today. When we come back for part 3, we're going to start talking about the different kinds of materials that we'll be using to hold on to our charge, because we're not going to be able to limit ourselves just to individual particles. We're eventually going to have to start working our way up to larger macroscopic constructs of charge. So we'll see you at video 3.